that much during the week. And then I am discussing a little bit the physics of the Fermi-Hubbard model, and then coming into the actual topic of the subject, which is the dipolar extended Hubbard model, and then discuss my results and come to a conclusion. So along this week, and also last week, we heard about dipolar gases and dipolar liquid, both from fermionic and bosonic atoms, and also dipolar molecules, but we have not heard a lot about dipolar atoms in optical lattices. And of course, we haven't heard about that because it's very hard to make. But as I am a condensed matter theorist, I'm here to try to convince you, all the experimentalists here, that although it's hard to do, it should be worth doing. And I'm trying to sell out even more that not only doing that, but on a particular regime of parameters that I have addressed, that it has very many different phase transitions, and it's really worth the effort to try to get there. So just a brief review. Here we have heard about, so I think the pointer is not working, but anyway, doesn't matter. So we heard about fermions trapped, but here on top of the trap, I want to address periodic potential that can be achieved by counter-propagating lasers. And the reason people like me who come from condensed matter theory want to do that is because we want to use this to explore many body physics that can be done with cold atoms. So quantum magnetism, as optic superconductors, topological materials, and many different things that can be studied in this platform. And the idea of using, oh, thank you. Okay, so the idea of using this platform is because we do have an enormous amount of control that we do not have on condensed matter systems. So you did not set the time there? Oh, okay, so I was 0 time. But anyway, we can, okay, we can control the interaction strength, the lattice hopping, dimensionality, and the shape of the optical lattices, and many different things that we cannot control in materials. So this is why people like me are coming more and more to conferences like that. So the idea is that we do have the same model to explain both the materials that are strongly correlated and have strongly correlated electrons. This one here is a particular cuprate, and we can emulate actually the same model that is used to describe these materials here in strongly in cold atoms interacting in optical lattices. And the model is the Fermi-Hubbard model here, the Fermi because I'm describing fermion cases, and mostly lithium and potassium are the atoms that are used in this case. And this is a very simple model that has a 2-term Hamiltonian. One is the hopping that leads one atom from one side to the next one. Exclusion principle makes it impossible to have 2 atoms within the same hyperfine state in the same site. And here, whenever they meet in the same site, we have an interaction strength. So although we only have 2 terms and also the density to control the system, this is a model that does not have an exact solution apart from 1 dimension. So it has been proposed in '63 to study magnetism, and as I just said, it has Bethe-Janssen solution in 1D, but no known solution in 2D and 3D, and that's why we are still struggling with it since 1963. So what's the physics of the Hubbard model? When we have 1 atom per site, what happens is if we don't have correlations, so the interactions are turned off, we have a half-fill band, but when we turn on the interactions, we open up a gap and we do have an insulating state that's very different from the insulating state we learn on a classical condensed matter first course when we learn about band theory. So this is what we get when we have correlations. And this has been measured like 10 years ago now from Ulrich and from Tillmans Esslinger's group. And the thing they used to see that was looking at the double occupation and see how it progresses. So this was observed in bulk, and more recently on site-resolved imaging, both in lithium and potassium in different groups. So this is well established now. And the other thing that the Hubbard model does have is antiferromagnetism, which is, besides having one atom per site, is that they are antiferromagnetically arranged. And so this has been observed in bulk, not long-range order, but magnetic correlations. And this was done by looking at the magnetic structure factor, but both theoretically and experimentally. And here, site-resolved antiferromagnetic correlations that have been recently appeared. And even long-range order in 2D systems, as from Marcus Greiner's group. So the point here is the remaining things we have to see is what happens when we cool down, and how do we do thermometry in these systems. And to do that, to reach ordered phases, we need to do that. So the point here is to make is that's not a closed issue. Much has been done in that, but there is still some things that need to be done, and going to even lower temperatures to achieving DNEL phase and possibly superconducting phases of half-filling. So all I have described this far was with on-site interaction and only U. And although this is interesting and there's a lot of physics in it, when we turn back to materials, is that enough to describe the physics of the materials, such as the cuprates and things like that? So the question is, should we care about long-range interactions, and what's the physics that lies when we do that? So one way to look at that is to look at the dipolar atoms in optical lattices, and this will lead to the extended Hubbard model. So here there are examples of dipolar atoms that have been used, fermionic dipolar atoms that have been used in gases, but not with optical lattices. And here, when we have a magnetic dipolar atom, what we have, of course, is a magnetic dipole. And here, the one in erbium is fairly big. Then in units of the Bohr magneton. And so we have dipole-dipole interactions, which are different than the ones we have in the Hubbard model, the usual Hubbard model, because they are long range and they are anisotropic. And they have this form here, so they roughly form with 1 over r cubed, and they depend on the direction of the dipoles regarding one another. And they can be both repulsive and attractive. And this is very interesting for theory. And here is the first example of extended Bose-Hubbard model with ultra-cold magnetic atoms. And so here are dipole atoms trapped in a lattice. The thing here, they are of bosonic nature. But anyway, things I want to show here is that all the dipoles here point in the same direction. And of course, they are bosons. So there is still no experimental realization of these systems with fermions, but it should be really interesting to do. So is it worth the effort? And I hope to convince you it is. So this is the extended Hubbard model where, oops, I'm confused here with the two hands. But anyway, here's the hopping term as we had before, and the on-site repulsion as we had before, and I have added here this one extended term. And this model has been studied when I and J are near neighbors, and it's just a constant V. And what we have in this particular case in 2D is, if we look at this phase diagram, if we have a large U, we have an antiferromagnetic state, which is 1 atom per site, and they are organized that spin up, and down this way. And if the near neighbor repulsion is stronger, as I show here, what happens is instead of having one atom per site, we will have 2 atoms per site and an empty site in between, and we'll form this checkerboard material. So if we play around with U and V, we can cross from an antiferromagnet to a checkerboard charge density wave material. So this is for the plain extended Hubbard model. So we see competition between charge and spin ordering, which is interesting. So when we have this dipolar exchange extended Hubbard model, what we have here is, I'm calling the green atoms in this hyperfine state the spin down atoms, and the red ones in the other hyperfine state the spin up atoms. And all the dipoles are pointing in the same directions, and the angles theta and phi that the dipole makes with the vertical here can be experimentally controlled by some external field. So as I said, the spin degrees of freedom, what I'm calling up and down, are just the hyperfine states as it is in the usual Fermi-Hubbard model. And here I have the charge degrees of freedom, who are just the position of these atoms in the lattice. So with this, I come to the extended dipolar Hubbard model, which has the same structures as before, but instead of having a constant and only near neighbor interaction, we do have a dipolar interaction of this form. So a disclaimer here needs to be made. So if I look at this interaction, of course it blows up at the origin and the interaction just goes to infinity. But Peter Shaw sat on my side on the bus yesterday, and he was telling me that, you know, he could think of some possibilities of screening so that Vij remains finite at the origin. And what I'm going to do is I will consider all the Vij at the II site to be U. So I'm just separating the next near neighbors or longer range order from the on-site, and the on-site will have whatever is on-site and the remaining VII also. So what I'm going to do is I am going to do calculations on a 2D systems with periodic boundary conditions, and I will do calculations on a 4x4 lattice, and I'm just using the hopping as my energy unit. So I'll set the hopping equals to 1, and I will also set U equals to AT. I'm not changing U around here. What I am going to change is V, the dipolar interaction, the angles theta and phi, and I will look for ground state properties of these systems. So what I am going to do as well is this interaction is long-ranged, so I am going to introduce a cutoff, and the cutoff will be from, I'll have near neighbor interactions, which are in the x direction, in y directions, and they can be different, and also along the diagonals. So I'm going to restrict myself to near neighbors and next near neighbors, and will cut off. But in doing so, I will preserve the effects of anisotropy and also some effect of longer range than near neighbors. Yeah. So it's periodic boundary conditions. This minimizes size effects. So we do Lanczos diagonalization, which is just a procedure to extract the ground state. We start with a trial function, and then we apply the Hamiltonian and look for a function psi1 which is orthogonal to it, and keep going forward and forward with this procedure. It's just a cute animation Thiago did, so I like it. And we end up with a tridiagonal Hamiltonian in this form, which, you know, saves memory from keeping the whole Hamiltonian, and the symmetries are incorporated, and it converges fast to the ground state if we choose wisely the initial guess for the wave function. So the size of the Hilbert space goes with 4 to the number of sites. As here we have 16 sites. It's fairly large. It goes to 10 to the 9. So to do this calculation, we do need to take symmetries into account, and we also do parallel computing. So the huge Hamiltonian, or 4.3 times 10 to the 9, is really big. But when we take into account that magnetization and number of particles, we break this into blocks. And if we consider translation symmetry that we had to, because of the size of the matrix, then we break some more, and then we solve this numerically. And the important quantities, the quantities we want to look at, are the occupation in each site, the double occupation. I think I've shown that this can be used to map if we have, has been used to map if we have a Mott state or not. Here, it will not serve as a probe to the Mott state because we have this checkerboard pattern that does have double occupation. Spin, of course, we want to see spin correlation, and local moment. And this is really what the experiments measure. This imaging, the quantum gas microscope does parity imaging. So when we look a picture just like that from Chuk's paper, we see that the center here of the trap looks empty, but that's not really empty. What happens is when you image this, you kick off a double occupation. So what this is actually measured here is the local moment. So whenever we have an up or a down fermion, we see a dot here. But when we have a double occupation, one minus the other, it's 0. So that's what's happening in the center here. And whenever it's empty, it's also empty. So this is what is actually measured in the quantum gas microscope. So we are, once again, looking at ground state properties, and we are going to look at spin-spin correlation functions, charge-charge correlation functions, this moment-moment correlation function, and also structure factors that can give us hints on what's the sort of the ordering of the ground state. So if we break up this interaction in terms along the x, y, and diagonal 1, which is the up diagonal and diagonal down 2, they look like that. So we have made some plots of what it looks like. So as we change phi and theta, it can change a lot. So I'm not sure you can see, but red is positive and blue is negative. So it goes from positive to negative. And we start looking at this problem by looking at theta and phi equals 0, everybody pointing up. And this is isotropic, so this is a nice test to start with. So if we look at 0, 0, which is this corner here, everything is red. So all the near neighbor and next near neighbor are positive interactions. And so when we look at the ground state correlation functions, we get that. Clearly, there is something going on at this value of V here. So we are keeping theta and phi fixed and varying V. And let's look at what happens here at the left side. So if we look at the spin correlations, we see that if we look at next near neighbor along the diagonal or two neighbors to the side, which is green, it is positive, meaning that the two spins are pointing in the same directions. But if we look at the red and black here, which are near neighbors in x and y directions, they are negative, meaning they are pointing in opposite directions. So this is clearly an antiferromagnetic state. Oops. And if we, so if we look at the other side, on the other hand, we see that spin correlations are going to 0, so we are killing off the correlations. But on the other hand, the charge correlations are increasing for second neighbors and second neighbors also along the diagonal. And they are going to 2, meaning that if we have a pair here, we'll have another pair in the diagonal or 2 sides to the left or right. So this is what it's telling us. So we see that as we increase V, we are going from an antiferromagnetic state to a checkerboard charge density wave state. And this is not surprising because this is very similar to the usual extended Hubbard model, but here we only added, the diagonal terms that are not present there. What happens is we change the position of this line a little, but not too much. But it's reassuring to see we find what we are expecting to find. And one note here, if we look at the extended Hubbard model at half filling, in 1D at half filling, and take a look at what happens when V is negative and U is also negative, we get very many interesting phases, such as the singlet superconducting, triplet superconducting, phase separation. So this is and here is a quarter filling. We have this also insulating charge density wave, superconductivity. So this is a hint that if we go not only look what happens when V is positive or negative, but also U, we can see interesting phases, more interesting phases as well. So I'm getting to the more interesting part, which is what happens when we do have actually anisotropic interactions. First, I'll start fixing theta and phi, and we'll vary the intensity of the interactions. And I'll choose of a different point than I did before. So I'll choose theta of pi over 2. So here we have positive interactions in the x direction and negative along the y direction. And when we look at the spin correlations, we see, once again, we do have some phase transition. Here it's very sharp. We see that along the x and y, we don't have symmetry as we have before, and we can think of an effective exchange interaction that is different because V is different along x and y interactions. And so for small v, we once again get this antiferromagnetic pattern, but with differences along x and y. And for large values of v, what we see is a charge density wave, but different than the checkerboard pattern we saw before. So if we look here, red, which is along the x direction, and blue, which is also along the x direction, are going to 2. So we have very strong correlations for along the x direction. But if we look in the y direction or diagonal direction, then they go to 0. So we have this horizontally striped pattern here when we have theta going to pi over 2. So I moved the dipole from the vertical direction to the x plane, and that's what happens. So I'm turning it one more. So instead of having it along the x direction, I'm introducing a phi here of pi over 4. So I'm moving the dipole to the side. And here it puts me kind of in the middle of here. So I have like this green, which is negative, but not as negative as the blue one for x and y. And I have positive along one diagonal and negative along the other, so more complicated interactions. And once again, I do see a very sharp phase transition. And for small v, once again, the antiferromagnetic order establishes. And as I do increase v, we go to yet another state where I have strong correlations along the diagonal and 0 correlations if I look to the side. And these are two possible states that, encompass this distribution of charge. So something strong along the positive diagonal, and then other stuff that could be double occupations or empty or in singly occupied sites along the other diagonal. So we could just see the effect of changing theta and keeping v fixed, and we once again go through different phases. The phases that have strong spin correlations are again antiferromagnetic, and here are for intermediate angles. And here for small values of the theta, we go from the checkerboard on this side to the other horizontally striped on the other side. So one other way to do that is look at the structure factor. So for antiferromagnetism, we'll look at the structure factor for spin correlations, and if it has a maximum at pi, then we have antiferromagnetic correlations. If it has a maximum of the charge structure factor at pi, then we have this checkerboard, and we can have striped horizontally or vertically oriented. So here, at looking at the structure factor, we see we go to checkerboard and then antiferromagnetic and then horizontally striped. And as we increase V, we see that this antiferromagnetism gets reduced here in the center until it disappears. So we can have a crossing from checkerboard to antiferromagnetic to stripe to checkerboard directly to stripe. And here is a summary of the phase diagram. So we have either a crossing when V is too high straight from one checkerboard to the other charge-ordered phase, or going through antiferromagnetism in the middle. And this is a phase diagram obtained within the atomic limit. So for very small or large theta, we only have the checkerboard phase. But if we have intermediate values, we go from all these phases horizontally, this kind of phase separated, other phase separated, antiferromagnetism and twisting in the middle. So many different phases. This is still work under construction because we really need to understand what these intermediate phases are. So, well, this moved a little. It's definitely worth the effort studying this dipolar atoms in optical lattices. So we go through all these different phases, antiferromagnetic, and very many different charge density waves that can be checkerboard, striped, or horizontally or vertically, and we might still have some phase separation going on here. And so by keeping U fixed and not letting the interaction explode at the origin, we allowed for a double occupation that allows all these charge ordering phases that would not be there if this was not possible. So by varying the angles, we have different ordered phases. And we can explore quantum phase transitions from one to the other. If we consider attractive, that could be some superfluidity. And thank you for your attention.